Hello everyone, today we are going to perform hydromechanical deep drawing in Ansys workbench. So this is the general deep drawing in which we have die, blank folder, punch and a blank. This orange part is a blank. So hydromechanical deep drawing, the only part different with the deep drawing is we have a water medium or fluid medium in deep drawing process. So that method is known as hydromechanical deep drawing. So what happens whenever the punch starts moving against the blank and gradually fluid pressure develops. Some part of fluid pressure gets applied to the wall of the blank. So this is hydromechanical deep drawing. So first we will use Ansys fluent to calculate this pressure generated so that we can apply same pressure in the structural part to get deformed blank. So let's start. So this is our Ansys fluent. I have already taken the geometry. So this is our fluid medium and this is our die, this is our blank, and this is the punch holder, sorry, punch, and this is the blank holder. So now under mesh, so first I just suppress this solid structures because we only want to perform fluid analysis in this fluid geometry. This is our fluid geometry. So I'll give sizing 4 mm. Generate. Okay, so the mesh looks good. Okay, now comes to name selection. So this is inlet part. So I'll say inlet region. That is where the punch contact will be there. And this one is as outer region. This one is outlet. A small 2 mm outlet. As this is a quarter model, so we have to give symmetry. This is symmetry 1. Other side will be symmetry 2. Symmetry 2. So this is the inlet region. So inlet region is the area corresponds to the punch area, and this remaining outer region covers the blank region. So apart from the inlet region. So if I, yeah, so our inlet region covers some part of the blank which corresponds to the punch area, and this outer region covers the remaining area of our blank. Suppressing the body. So this is outer region and this is the outlet, symmetry 1, symmetry 2. So now closing the window, update, under setup, double precision. So gravity minus 9.81. So the time is steady state or transient. So one can use steady state or transient state. So any method will be good enough to generate a result. So under model, changing laminar to viscous model, changing from laminar to turbulence model. So the material I am using is castor oil. So I'll say castor oil. (965) is the density and 0.8 is the viscosity. Under Celsius condition, fluid, edit, castor oil. Okay, now under boundary condition. So this is inlet region. So here we are going to give velocity 10 meters per second is the velocity. In the real case scenario, there won't be fluid velocity like fluid inlet velocity that is 10 meters per second. There won't be any velocity. So the only velocity it will have is the velocity whatever the punch is having. So if the punch is moving 2 meters per second, the velocity at the top inlet region at the same corresponding at this top surface, the fluid will also supposed to move at 2 meters per second. So whatever the velocity of a punch is, but it is a one-way FSI, fluid structure interaction, that too in a one-way FSI. That is the reason we have to uh, take one assumption that punch is moving with 10 meters per second as well as the fluid is also moving 10 meters per second. So we have to give individually this fluid velocity so that we can get the fluid results, fluid pressure results at the interested area. So that is the reason that is the only reason we are giving 10 meters per second. But if we use two-way FSI, we don't need to give fluid velocity because that will be in that case the whatever the punch is moving with that punch it will apply some pressure to the fluid medium, and with that sense we'll get the fluid pressure. So this is inlet region, outer region no need, and the outer region is the wall, pressure outlet, symmetry, symmetry. Under monitor I am changing the residual from default 1 power minus 3 to minus 6. So initialization, hybrid initialization, 0.0015, 20, 300. So per time step 100. So for total 20 time step 2000 iteration, number of iteration. So I'll say calculate, calculate. So now okay, now it is calculating. So 2000 iterations have completed. So if you see at this residual part, the graph isn't changing the much except for k. The all the remaining variables continuity x, y, z, and epsilon. Those graphs are not changing much. So that's the reason one can take steady state or tangent state. Okay. So I have taken transient state. So since there is no change in much changes in the graph, so that's the reason I have taken 20 number of time step. So since there is no much changes in the graph residual part, so that is the reason I have taken 20. Even if I take higher number of time step like higher like 50, 100, the graph won't change much. It will stabilize it somewhere. It will stabilize. So that's the reason I have taken only 20 number of time step. And with the finer mesh, this graph will stabilize uh, quickly, more quickly. If you use good quality of mesh now, Now let's see at the result part. Inlet region, pressure. So this is the pressure at outer region. So this is the pressure at outer region. So we are supposed to import this pressure in the static structural part. So I'll set up